Okay, good morning. Today I know classes have been canceled. Oops, I have some feedback going on. So I know that we have classes have been canceled until the 31st of March, and then classes will resume on the 1st of April after that. So in light of that, I won't be teaching any new material at this moment. Instead, what I was planning to do is basically write out some solutions for exercises in section 6.2, integration by substitution from TAN's calculus textbook. So basically I was going to be pretty slow today in terms of what I was going to do, because I was going to, if people are following along, I would just kind of let them work it out, and I would be working alongside with them, and hopefully we would be getting the same answers. So we'll start off with, make sure I'll keep the page as straight as possible. So we'll start off with exercise 1, and we have the integral of 4 times 4x plus 3 all to the 4th, I think that's the 4th, yep, dx. And we have to use our rule of substitution. So again, we pick a part that's probably the most complex part. So we have this, and we're going to let the inside of this to the 4th be u. So we let u equal 4x plus 3 and then we differentiate so that I get 4. So 4x, and when we differentiate that just becomes 4. The 3 is a constant times dx. So what we notice is that I'm going to just rewrite it over here. So I got 4x plus 3 to the 4th times 4 dx. Because right here, inside of this is u to the 4th, and this part here is the du. So here's du. And now I can integrate that. I have 1/5 u to the 5th plus a constant. And then at that point, we have to put back our original variable. So the u goes in here. So I get 1/5 4 to the x plus 3 all to the 5th plus a constant. So there's my solution for that, and yes, it does match what they wrote in the back of the book. Okay, so number 2 is also very similar. I have the integral of 4x, all multiplied by 2x squared plus 1, all to the 7th dx. Same thing again. The more complex part of this is inside the to the 7th part here. So this is what I'll let that equal u. So u equals 2 to the x squared plus 1, and then I differentiate. And just for make sure that everyone's following along, I'll rewrite this so that I have here to the 7th, I have 4x dx. Now again, that part is u, and this part right here is the du. So if I integrate that, that's u to the 7th du. Oh, gotta make sure that I don't clip off the question. Which, when we integrate that, becomes 1/8 u to the 8th plus c. And then our final part is substituting in the u back in. That's it. Okay. Ooh, this is harder for me to read. I think that's, let's see, number 3. So this one looks a little harder, but the more complex part again is this term that's squared. So again, that's what I'm going to let be equal to u. Okay, so I'll let that equal u. And we differentiate that, so differentiating the x cubed becomes 3x squared, and the 2x becomes just minus 2. And this is all to the dx. Okay. So now I can start to replace that. So inside here is the u, and this part is my du. So inside here I have 2 squared, or sorry, u squared du, followed along with, now we can integrate that, so I get 1/3 u cubed plus c, and then this is equal to 1/3 x cubed minus 2x to the 3 plus c. And double check. Yes. Oops, move the paper over. Okay. Move that out of the way. So we did 3. What's 4 looking like? Okay. So with 4, I have the integral of 3x squared minus 2x plus 1. Then the next one I have x cubed minus 2x, x squared plus x all to the 4th dx. So again, this is the more complicated term, so that's what I'll let the inside of this to the 4th be. So I'll let u equal inside of that. So that's basically inside here is what I'm letting that equal to u. So here's the du. And so again, differentiating that. So this x cubed becomes 3x squared minus 2x all to the dx. Oh, and I forgot to differentiate this x right here, so that's plus 1 there. And that's good because let's pull out a different pen. This is what's going to be my du. So again, I can just replace that now. So I have the integral of u to the fourth, and the du, this is equal to the 3x squared minus 2x plus 1 dx. So I can just simply write du. And that becomes 1/5 u to the fifth plus c. And now I can substitute in what I had originally for u. We're done that one. That's 4. Okay, so now we can move on to the fifth one. This one's different. It's got it's a rational function. Okay. So again, the more complicated part of this is around this part all cubed, so I'll let that equal u. So again, let u equal 2x squared plus 3, and differentiating that I get 4x, and the plus 3, that it's a constant, so when we differentiate that, that's a 0, so 4x times dx. So that means this part right here is my du. So what I'm going to do, just to show that a little bit clearer, I'll split that up. So I can write this 1 over 2x squared plus 3, all cubed, and I'm going to times this by 4x dx. So this part right here, that's du. This part right here is u. So if I integrate that, I get 1 over u cubed times du. At that point, I can integrate that. I'm just going to rewrite that so that I got u to the minus 3 du. And when I integrate that, the exponent goes up by 1, and also we have it in the denominator of the fraction here, 3 plus 1 as well. So minus 3 plus 1 gives me minus 2. And minus 2 here. Which is also equal to minus 1 over 2u squared plus c. And then, oh, I've gone too far up. I need to replace the u back in, so, or take that and put it back in. So minus 1 over 2, replacing the u. And there's our final answer for 5. So let's see if I matched what I had in the back of the book. And I do. Perfect. So that's 5. Try with 6. So that's page 3. So the more complex part of this integral is right around here. So we'll let that probably equal u, and hopefully that works out. So there's the u, x cubed plus 2x. And if we differentiate that, that becomes 3x squared plus 2. That's all dx. And again, just to show this off a little better, here's our du, and inside here is our u. So I get the integral of 1 over u squared du, and that's equal to the integral of u to the minus 2 du. And same thing again. The integral goes up by 1, and we also have to put it into the fraction here, into the denominator. So this becomes minus 1. This becomes minus 1 as well, plus c. So I get minus 1 over u. That's equal to 1 over, and then I substitute in what I originally had for u, which was x cubed plus 2x plus c. Okay. All right, let's do number 7. So the integral of 3t squared to the square root t cubed plus 2t, or plus 2, I'm just going to make sure that I think so. Yep. dt. Okay. So the more complex part again is inside here. So let u equal t cubed plus 2. Then we do the du. 3t squared dt. And that's good because I have this term in the dt right there, but I can just rewrite that out just in case people are watching this or reading through the solutions later. Okay, so then what I'm left with here, after doing my substitution, I get the square root of u du. I'm just rewriting it so I have a exponent. Okay, and it goes up by 1. So I'm left with 1 half plus 1, so that is 3 halves du. And over here is going to be 1 over 3 halves. And again, 1 over 3 halves is equal to 2/3 u to the 3 halves plus c. So again, let me just, for some people over here, I have 3 halves. That's equal to 3 times 2 to the minus 1, which again, with a negative exponent, it flips. So, just to clarify on that, so again, if you had something like 1 over, and I had like 3 times 2 to the minus 1, again, the minus, if you wanted to get rid of the negative exponent, you move it into the numerator. So it becomes 2 over 3. Or if I had 3 times 2 to the minus 1, I want to get rid of that negative 1 as a fraction. Well, I just move it into the denominator. So in this case, this becomes 3 over 2. Okay. I'm almost finished. So all I have to do now is substitute in my u. So I got t cubed plus 2 all to the 3 halves plus c. And so let me check what I have for 7 for the answer. And I'm good. Here. Okay, moving on to 4. Number 7. I guess I could do number 9 or number 8. I mean, yeah, okay, I'll do 8. So the integral of 3t squared multiplied by t cubed plus 2 all to the 3 halves dt. And so again, this is the more complex term. I'm going to let this inside of the 3 halves be u. let u equal t cubed plus 2. We differentiate that. Just going to rewrite that so that I can group just a little better. So here is my u, and then my 3t squared dt. That's my du. Same thing, 3 halves plus 1. So 3 halves plus 1 . Okay. Which means that over here is 5 halves making sure not I'm trying to not skip any steps, so I'm left with 2 over 5 or 2/5, and I substitute in my u. Plus c. Okay, so we're good so far. We've done 8. Let's do 9. I think after a while you kind of get a hang of this, that you're just kind of looking for kind of the more complicated term in the integral, and you just have to make sure that when you differentiate this, now they've thrown a little bit of a curveball now, because now when I've set x squared minus 1 to be u, and I differentiate this, I get 2x dx. And over here, I have only x dx. So what I need to do, I need x dx. So I need to solve basically for x dx. So I need to get rid of this 2 here because it's not very useful. So what I can do is divide by 2 on both sides. And that leaves me with 1/2 on this and x dx. So again, for those that are kind of watching this later, or really what I did was this 2d . Okay, so in this part over here, that's not equal to du anymore, but it's equal actually to 1/2 du. So I get the integral of u times 1/2 du, and you don't have to worry too much about that half, because by our properties of integration, I can actually pull that out in front. Because again, it's a constant. So again, the exponent goes up by 1, and it's also, we put that number in the denominator in front, plus a constant. So now I'm left with 1/4, because 2 times 2 is 4, u squared plus c, and then substituting back in for u, which was our original x squared minus 1, and there's our final answer. And do I have the same? 9, number 9. Oh no, I made a mistake. Because I didn't match what I had at the beginning. So what did I mess up on? I forgot to do this correctly. So what I'm going to do is I'm going to scratch that out. So now what do we do now? Again, integrating. The exponent goes up by 1, so that's 10. 1 over 10 plus a constant. And then 2 times 10 is 20, so it's 1/20th. U to the 10th plus c. And then we follow that up with 1 over 20. And we substitute in our u. So in this case it is x squared minus 1 to the 10th plus a constant. Okay, so we'll do skip 10, let's do 11. So in this case I have to do the integral of x to the 4th divided by 1 minus x to the 5th dx. Okay, now there's kind of a complicated part. What do we do? Well, nothing inside of to the 5th or to the 4th is very difficult. It's just x. A more complicated function. I'm just thinking now. We're thinking like a rational function. And a rational function, it's just a fancier way of saying, oh, it's a fractional or whatever. There's a fraction, a function, and so I have something like f over g, and in this case it's this part right down here that's the more difficult part. So I'm going to let that all equal u, and we'll see what happens. If I do that, I get this. I get u equals 1 minus x to the 5th. And then when I differentiate that, the 1 is a constant, so it's 0 when we differentiate that. And then I'm left with minus 5x to the 4th dx. Now, again, I'm going to split this up so that we can see this a little easier. I can replace that with u. But now, at this part, this has to equal what I'm going to substitute in here. This is definitely not the same. This is not equivalent to du, because du is equal to minus 5x to the fourth dx. And what we'll have to do is I need to get it to be x to the fourth dx. I need to solve for that part. So what would be nice is if that minus 5 disappeared. And the way that we can do that is by dividing both sides by minus 5, so that I get 1/5. So minus 1/5 du equals x to the fourth dx. And good. That is what I'm going to substitute in for it. 1/5 du. So I'm left with 1 over u times minus 1/5 du. And I'll bring that 1/5 out in front of the integral. So I'm left with 1 over u du. And we have a special rule for the integral of 1 over u. That is ln. There we go. And substituting in for our original u, so that is 1 minus x to fifth plus a constant. Okay. Done 11. Let's do 13. Same idea. The more complex part is kind of this denominator here. So if I let that equal u, and I differentiate that, then that just becomes 1. And that's dx. So let's do that. Let's do that substitution. So I get 2 over u du. And I don't have to worry about that 2. I can actually pull that out in front. So it's the integral of 1 over u du. And if I use my rule of integration, then that's just the ln of u plus c. And substituting in my u back in, I get x minus, 2 ln x minus 2 plus c. And 13, yep. Now in the book, okay, so in the book, what they have is they have ln of x minus 2 squared plus c. What does that, it's not matching it, right? But no, actually, because of our rules of logarithms, you can actually pull that up to the top. So I get ln the absolute value of x squared plus c. But remember that when you take the square of an absolute value, it becomes positive. Right? Again, if I took let's say minus 3 and you squared it, that's equal to 3 squared, which is equal to 9. And also if I put in minus 3 in here and squared it, this still becomes 9. So you can also bring that 2 up to the top, and we finish off with x minus 2 squared plus c. Okay, so that's what we have. So now we match the back of the book. Here's 6, 13, 14. Let's do 17. And again, I'll let that equal u. And if I differentiate this, I get 6x dx. So again, just to show this a little better, what I would like to be able to replace here is with this by du, but the du in fact is 6x dx. So I need it to match what I want to replace here. So again, divide by 6. I get 1/6 du x dx. There's my u. So I have my integral of 1 over u times 1/6 du. And I can pull that 1/6 out in front of the integral, so I get 1 over u du. And this is our integral rule, which is 1 over u. If I integrate that, that becomes ln u plus constant. So 1/6 ln, and then I substitute in what I had assigned for u, which was 3x squared minus 1 plus a constant. And that's good enough for them at the back of the book, so that's good. Let's do 19. Okay, so we know that the integral of e to the x dx is equal to e to the x. But we can't just apply it blindly in this case, because it's not the same rules. I have a minus 2x. So what I'm going to do is I'm going to let u equal minus 2x. And when I do that, I differentiate that so that I get minus 2 dx. So what it would be nice to do is this would be equal to u, right, this part in the exponent, and I'd like to be able just to do a straight substitution for dx. So again, solving for dx, bringing it over to the left-hand side here, or so here is where it will become minus 1/2 du. So rewriting that, I have the integral of e to the u times minus 1/2 du. Bring that out front of the integral, so you get minus 1/2 e to the u du. And now I can just use my original rule here. So I get the minus 1/2 excuse me. And then substitute that back in. And there's my final answer for 19. And yes, it does match what they have at the back of the book. So I'll move that back up. So I have 19, let's do 21. So again, integrating it, e to the 2 minus x dx. And I'll let, again, complex part right here is that 2 minus x. Then I have the du. If I differentiate this, that's 0 minus 1 dx. I'm going to bring that over, dividing both sides by a minus, so I get a minus u dx. So that becomes e to the u minus du. Bring that minus in front, so I get e to the u du. And replacing the u now, so e to the 2 minus x. Oh. Plus c. Let's do that again. I've made mistakes before. So again, if I integrate this, e to the 2 minus x dx, we let that I can bring that negative in front of the integral. And then integrating that, so I get e to the u plus constant. And then replacing the u in this case, which is 2 minus x plus c. And that's what matches at the back of the book, so that's good. We're just rolling through all these exercises now. 23. Okay, so again, this looks like the most complicated part, that we will let that equal u. So the minus x squared. And when I differentiate that, I get minus 2x dx. And what I need it to be equal to is the x dx. So I'm going to manipulate this so that I divide by minus 2, so that I get the minus half du, and I'm left with x dx. So again, right around here, that's equal to minus du. And this part right here, that's equal to u. So e to the u times some minus a half du. And I'm going to pull out that minus a half in front. And integrating that, e to the u is still e to the u plus a constant. And now I'm just substituting back in what I originally had for u. Plus a constant. So 23. And I match. Good. I have the integral of e to the x minus e to the minus x dx. So the first thing that I can do is split that integral up so that I got e to the x dx minus the integral of e to the minus x dx. I can solve this easily because I have a rule for that. Minus there's some constant here. Now what I'll do over here on the side, I'll do e to the minus x dx. Again, we don't have that rule, but we'll let u be the complicated part here, which is the minus x. And if I differentiate that, I just get a minus dx. And I need to replace the dx, so I'm going to bring that negative over to this side. So when I do e to the u minus du, I can bring that negative out in front, and then substituting in what I originally had for the u here. So I get, well, when I integrate this, I get minus e to the u plus a constant, and then substituting that back in, minus x plus a constant. So what I do is now I can plug that back into right I had over here. So I have a minus and a minus, so that becomes positive e to the minus x plus a constant. And there's my final answer. Do I match in the back of the book? Yes, yes I do. Perfect. Okay, so if I did 26, we can break that up into two different integrals just by using our, I think it's our second property. The integral of the sum of two functions is the sum of the two individual integrals. So, and just as a reminder, so it's like the integral of f plus g dx is equal to the integral of f dx plus the integral of g dx. And that's just a property. So I'm going to treat these as two separate integrals. Like this is basically they've shoved into exercises in one. So what you could do, let's see, I'm just going to write it over here. What I'm going to do is let u equal 2x, which means that if I integrate this, this becomes 2 dx, and I need that dx to be equal to just, I need to isolate for this, so I need to solve for dx. So there, I can replace the dx I got the integral of u du times 1/2 du, 1/2 times the integral of e to the u du, 1/2 e to the u plus the constant e to the u 2x plus c. Okay, yeah, so I'm done for that one. I'll switch to a different color here. So let's say like here's 1. And I'll do 2 over here. So the integral of e to the minus 3x dx. So I'll let the u equal the minus 3x. And if I integrate that, that becomes minus 3 dx. And again, I need to isolate for the dx, so I bring that minus 3 over, so it becomes the minus 1/3 du dx. So when I integrate this, it becomes e, and we're doing my substitution, e to the u times minus 1/3 du. I can factor out that 1/3, so I get minus 1/3 the integral of e to the u du. Okay. And now, putting that all together, our final answer should be for the first integral, it's 1/2 e to the 2x plus, minus 1/3 e to the minus 3x plus a constant. And what is 20? Oh, 26 doesn't give us an answer. And that looks right to me, so we'll carry on. Okay, moving on. We did 26. Let's do 27. Okay, so again, I'm going to replace the denominator with u, so let u equal 1 plus e to the x. If I differentiate that, the 1 is a constant, so it's 0. And I'm left with dx, sorry, e to the x dx. Split this integral up so that I can show you better. Which means that here, this is going to be du. So when I do my substitution, it's 1 over u du, which we know is ln u plus a constant. And then doing my substitution back, so my u is equal to 1 plus e to the x. And that's it. In the back of the book, they wrote this slightly different, and they said, we know that well, first of all, we know that the function e to the x is always greater than 0. Over the entire real number, and translating it up, so if that was crossing at 1, this is going to be crossing at 2, e to the x plus 1. Is still greater than 0. For the entire. So again, since this is always positive, there's no point in having the absolute value function applied to here. So again, we can just drop that. Just a little simplification. Oops. And we're done. Okay. So 27. 29. Okay, that's pretty nasty. So I'm going to say the more complicated part again is right around here. It's in the denominator, or in the numerator here. And I'm just thinking, as if I set that equal to u, what the derivative will look like. And so if I do that, so again, it's the derivative of the outside, which again is e to the x, and then I need to take the derivative of the square root of x. Just quickly, I know that if I take the derivative square root of x, that's 1 over 2 square root of x. So dx. And I don't quite like that. Let's try a different one. So did the derivative of that. And I isolated for dx, then I would have the square root of x du that might work. Okay, let's try that. So, let u equal the square root of x. And, again, okay. Hopefully I don't have to do the derivative of the square root of x, but again, like, all right. Okay, so now what I'm going to do is I'm going to do the substitution. So I have e to the u over so I have just dx, so I need to isolate that, so I'm going to have 2 square root of x du is equal to dx. So I'll replace that in, so I got the square root of x times 2 square root of x du, and I'm going to cancel out those square root of x there, so I'm just left with the integral of, and I'm going to bring the 2 out in front of the integral, so I got 2 times the integral of e to the u du, and then the integral of e to the u is e to the u, and then substituting in what we had originally for u, which was the square root of x, plus c. And perfect. That is the correct answer. So like you saw, I was kind of going through quickly in my head, you know, oh, if I picked u to be this top part, what does the derivative look like? Could I cancel out something? No, this one didn't work out. Then I tried this quickly, and this seemed to work. So that's what we did. And we were able to cancel out that square root x. I was able to bring out the 2 and reduced it back to a rule that we already knew, and we carried on. Okay. That was me forgetting to plug in the camera into the wall. And then it ran out of battery. Okay, so 31. Okay, so what I had thought, so what we'll do here is we'll let u equal this complicated part in the denominator. And then we differentiate. So that becomes e to the 3x times 3 plus 3x squared. So that becomes 3 times e to the 3x plus 3x squared times dx. And then the way that we'll get around to try to match the numerator, I don't know why I didn't see this sooner. You can factor out the 3. Bringing the 3 over to the side. Frig. Okay. So then just split that up. And here is u, and here is 1/3 du. So that is equal to the integral of 1 over u to the 3, so u cubed, times 1/3 du. I can factor that out, so I get the 1/3, the integral of 1 over u cubed du. I don't know why I didn't put it into the denominator immediately, but here it is. So that I get... Oh, and then I need to substitute in what I had originally for u. So in this case, I had... Can fit that all on the screen? Oh, kind of. Barely. There. And did I match with... Yes, good. Yeah, so in this case, didn't work out. So again, the trick for this was to factor. Oops, I should have put that up there. Okay. So it did 31. Let's do number. Let's do 33. E to the 2x times e to the 2x plus 1 all cubed dx. So I'm going to let inside here equal u. And if I integrate or differentiate that, I get e to the 2x times 2 dx. So du is equal to 2 e to the 2x. And I'd like to have this part and this part be the same, so 1/2 du is equal to e to the 2x dx. So doing my substitution, inside here is u cubed times the 1/2 du. Then the 1/2 comes out in front. And now I can integrate that. So that becomes u to the 4th, and then the 4 comes down into the denominator, plus a constant. And then 2 times 4 is 8. And then substituting in what value, or the function that I had for u, which was e to the 2x plus 1, all to the 4th plus c. And good, that's what is at the back of the book. Okay, so then the next one is, switch to that one, 33. So I think what I'll do is this is the more complicated part right here. So I let u equal ln of 5x. Then what I'm going to do is I take the derivative of that, which is 1 over 5x. So the derivative of ln x is 1 over x, and I also need to do the chain rule, so I need to also differentiate on the inside. So when I take the derivative of 5x, that's just 5. So all dx. And then the 5's cancel. So I'm left with 1 over x dx. View. So just splitting this integral up a little bit, I have ln 5x times 1 over x dx. That's equal to du. So now I can do the integral of u, because this whole thing is u, du. So if I integrate that, that goes up by a degree plus the constant, and then I get the 1/2 times u, so in this case it was ln 5x all squared. Now, let's see, 35, yes, and that's it.